Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face trending list, published on August 1st, 2025, so about 4 days ago. This survey reviews the state of the art in a field where models can now segment objects based on audio cues with over 92% accuracy on some key benchmarks. The paper is titled Multimodal Referring Segmentation, a Survey, and it provides a fantastic overview of how this technology works across images, videos, and even 3D scenes. It essentially covers the major architectural shifts and performance gains driven by models like transformers and LLMs. Alright, so this figure really clarifies the core task. You have a referring expression on the left, which is just a human instruction, like text or audio. In the middle is the visual scene. And on the right is the model's output. For instance, with a simple image, the text, "the young man in the red hat," leads to a precise mask around just that person. This is called referring expression segmentation. But it gets more complex. For video, it can track a moving object. And in the omnimodal example, it even combines audio and image cues. So the authors lay out this really helpful roadmap for the whole field. They start by proposing a unified meta-architecture, which is basically a general blueprint for these models. This includes key steps like feature extraction, where the model pulls important details from the data, and multimodal interaction, which is how it fuses the visual and language information together. From there, they dive into the specific methods used for images, that referring expression segmentation, and then move on to video and even 3D scenes. Building on that, this figure highlights a key advance called generalized referring expression segmentation. You see, a classic model could only find a single object. So for an instruction like people with long hair, it fails, because that refers to two people. The generalized method, however, correctly identifies both. It can even handle cases where the object is not in the image at all, like girl wearing a brown leather jacket. The generalized approach correctly returns an empty result, which is a huge step for real-world reliability. Okay, so to train and test all of these different capabilities, researchers rely on a really wide range of specialized datasets. This table lays them all out, organized by the type of scene, from standard images and videos to more complex audio, video, and 3D scenes. For instance, the image scene section lists benchmarks like Ref Coco, with nearly 20,000 images and over 140,000 expressions. And then, connecting to our last point, the GRX section at the bottom details the dataset specifically for that generalized task we just discussed. So how do the models actually work under the hood? Well, this figure breaks down the two main architectural paradigms. The top diagram shows the traditional two-stage method. Here, the model first identifies all possible objects in the scene, like both the cat and the dog, and then it separately matches the text description to one of them. In contrast, the more modern one-stage method, shown at the bottom, is more direct. It fuses the image and text information together from the start, generating the final mask in a single, end-to-end step. Moving to the results. This table provides a massive performance comparison on standard benchmarks. You can really see the evolution here. If you look at the top section, with conventional methods, you can see a steady climb in performance over the years. But then, the real leap comes when you look at the bottom section, which details methods based on multimodal large language models. These newer models, like M2 SA13B, are pushing the state of the art, achieving some of the highest scores. Alright, so looking back at everything we've discussed, it's clear this field is moving towards more robust and generalized models that can handle complex real-world instructions. And a huge driver of that progress is the power of newer architectures like transformers and multimodal large language models. That's it for this episode.